I'm Sean Carroll from Caltech, California Institute of Technology, and I want to close things up by asking a slightly philosophical question about what really counts as an observer. We think we know what counts as an observer. We see ourselves observing things, other people observing things, but implicitly we have a lot of baggage there. There's a lot of things we think that are properties of observers, one of which is not only does an observer see things, but the things that the observer sees are remembered, are recorded. We could then ask that observer what they saw. In some sense, they're reliable. In a multiverse context, this concept of being a reliable observer is a little bit trickier than it might otherwise be. So let's think about the fact that we remember things, that we have records. How do you know that things happened in the past, right? You think that you know that the Golden State Warriors won the NBA championship last year. You think you know that there were other kinds of animals in the world hundreds or thousands or millions of years ago. How do we know these things? Well, we have memories or records. We were at the game, or we saw a photograph of this event happening, or we see a fossil record. So what does that mean? There's some correlation between an object right here and now and something that happened in the past. That's what a record or a memory is. Interestingly, there are no such correlations between objects here and what happens in the future. You can predict the future, but no one has a photograph of the future, a fossil of the future, or a memory of the future. So why is that? Again, we tend to think of it as just obvious, but the laws of physics tell us differently. In the fundamental laws of physics, as far as we understand them, there is no difference between time moving toward the past and time moving toward the future. We typically ask a question like, if 2 billion balls hit each other, what angle do they bounce away at? But we could equally well, according to the rules of Newtonian physics, give the final configuration with the balls moving away and ask where they came from. Information is conserved from moment to moment as far as we understand the most fundamental laws of physics. So why is it that we have some access to the past in the form of memories and records that we don't have toward the future? That's what we call the arrow of time, or one particular version of the arrow of time, the difference between the past and future. And ultimately it comes down to the existence of what we call entropy. Roughly speaking, entropy is the messiness, the disorderliness, the randomness of a configuration of stuff. Back in the 1870s, Ludwig Boltzmann, an Austrian physicist, made that a little bit more rigorous. He said that when you look at something like cream mixing into coffee, you don't see all of the individual atoms and molecules. You see some gross features of the system. There are many different individual arrangements of the individual parts, the atoms and molecules, that would look the same to you. And entropy, Boltzmann tells us, is just a way of counting those arrangements. Entropy counts the number of arrangements of atoms and molecules that would look the same macroscopically. So from that perspective, it's perfectly obvious why entropy increases with time. There are more ways to be high entropy than to be low entropy. But there's a problem. That tells us why the entropy of the universe will be bigger tomorrow than it is today. It doesn't tell us why the entropy was lower yesterday than it is today. That is a problem for cosmology. And right now, the state of the art is the following. That's just the way it was. That's the best we can do right now. We say that as far as our best understanding of the universe is, it started in a very low entropy state, 14 billion years ago near the Big Bang. This is what is called the past hypothesis. Why was it like that? Nobody knows. Some of us have ideas. I have ideas. Other people have ideas. They're different ideas. There's no agreement. This is a wonderful problem to think about if you're a cosmologist. But the good news is, once you take that assumption, the early universe had a low entropy, we can explain things like, why do you remember the past and not the future? Why do we have memories or records? Here's an example of a memory. My favorite example is an egg broken on the sidewalk. You don't think of it as a memory, but if you ask yourself, what is the future of that egg likely to hold? There's many things that can happen. It can wash away in a rainstorm, it could be cleaned up by somebody, or it could just sit there and fester. But if you said, what was the past of that egg probably like? With overwhelming probability, you think there was an unbroken egg and somebody dropped it and it broke. Somehow you think you know more about the past than the future on the basis of the existence of this broken egg. Why is that? Again, it's not the fundamental laws of physics' fault. Given that egg lying on the sidewalk, the number of things that can happen to it in the future and the number of ways it could have been created in the past are exactly the same in number. The difference is that toward the past, we know something else. We know something we don't know about the future, namely, the past had a low entropy. That picks out, as much more probable, some of the trajectories that could connect the very early universe to the egg. The point is not there's only a few number of ways to make an egg. The point is that given the low entropy of the early universe, the overwhelmingly likely way to make a broken egg is to start with an unbroken one and to break it. That is the origin of memories and reliable impressions that observers have about the past. We don't have any such thing about the future. There's no future low entropy condition. That's why we remember the past but not the future. The problem is, or the fun is, that maybe we could imagine living in a universe that didn't have a low entropy past. And in fact, it was Boltzmann himself who first contemplated this possibility. He said, what if the universe was just high entropy everywhere? What if it was just a gas of dust? He didn't know about the Big Bang or quantum mechanics or anything like that. So he said, imagine a gas uniformly spread throughout the universe. It would randomly fluctuate all over the place, and occasionally it would come into apparently unlikely low entropy configurations. They were rare, but you have infinitely long to wait. Lots of rare things will happen. A consequence of that, if that was what the universe was like, is that you could fluctuate randomly not only into gases of dust in little balls, you could fluctuate into observers. The minimum, easiest to make kind of observer is what is called a Boltzmann brain, a random collection of particles that assembles itself from the surrounding chaos into the form of a brain just long enough to look around and go, ha, empty space in thermal equilibrium, and then it would die. So if Boltzmann were right, if this were the way the universe was, we would predict with overwhelming probability almost all observers would be these randomly fluctuated Boltzmann brains. Now the good news is, it doesn't have to be that way. Even if we live in a multiverse where there are random fluctuations, you don't need to have Boltzmann brains at all. But you can. There's different cosmological models. This is part of our job as working cosmologists to figure out why is the universe one way or the other. What is the universe like beyond what we see? In some models of the multiverse, almost every observer is a randomly fluctuated Boltzmann brain. In other models of the universe, most observers are like you and me, ordinary observers. You might have heard that even in the vacuum of empty space, there are bubbling virtual particles called quantum fluctuations. You heard wrong. That is nonsense. As you heard in this documentary, what quantum mechanics says is that if you're not looking at a system, it looks like a wave. When you look at it, it looks like a particle. The equivalent of that for empty space is, when you're not looking at empty space, it's just sitting there in a wave-like vacuum configuration. Nothing is happening. Were you to look, you would have a non-zero probability of seeing an observer, a brain, a galaxy, or whatever, but as long as you don't look, there's no observers there. Nevertheless, there are other models where there really are all these random fluctuations. They can bring these observers into existence. What do we do about that? What can we say? Do we rule those out, or do we say, well, most of the observers in my universe are random fluctuations. Thank goodness I'm not one of them. The most common strategy is to say, no, we can't accept universes with randomly fluctuated Boltzmann brains for a simple reason. Here's the reasoning. If most observers in the universe were Boltzmann brains, I would probably be a Boltzmann brain. I am not, I assert, a Boltzmann brain. Therefore, most observers in this universe aren't Boltzmann brains. The correct theory of cosmology must be one in which most observers are ordinary observers. The problem is, the statement, I am not a Boltzmann brain, is just what a Boltzmann brain would say. Not most Boltzmann brains, admittedly, but most observers who are just like you would say that. In other words, not only are there random fluctuations into Boltzmann brains in these big fluctuating universes, but there are so many fluctuations that even if we specialize to observers just like you, people who are sitting in a room like you're sitting in, with the memories that you have in your head, the impressions of your past life and so forth, the overwhelming majority of those observers recently randomly fluctuated into existence. And under the reasoning I just gave you, they would be wrong. They would live in a universe with Boltzmann brains, but they wouldn't know it. Can we somehow do better? I think we can. I think we can do better. Here's my suggestion, and it gets a little philosophical, so you can take it or leave it, but I think it gets us out of the conundrum we've put ourselves in. As we said, if the universe were dominated by Boltzmann brains, if most observers randomly fluctuated into existence, then you and I would probably be Boltzmann brains. And it's not that I know I'm not, but if I were a Boltzmann brain, everything I think I know would have just randomly fluctuated into my brain. It would not actually be a reliable memory of the past. There is no past low entropy boundary condition. This includes everything I think I know about Boltzmann brains, including what Boltzmann brains are, why they exist, how probable they are, etc. So if this were the universe I lived in, if I lived in a universe where I said most observers are random fluctuations, I would know right from the start I have no good reason to believe I lived in a universe where most observers were random fluctuations. This is a situation which is called cognitively unstable. It cannot simultaneously be true and you have a good reason to believe it's true. Therefore, the only strategy that gets us through the day is to say, no, I'm not going to even contemplate that kind of cosmology. When I sit down and think about all the different ways the universe can be, I will only give any credence to those ways in which most observers are ordinary, reliable, come in ordinary thermodynamic ways from a low entropy past. Otherwise, I can't say anything at all about the universe that is correct. So we don't know what the correct theory of cosmology is, but this way of thinking about observers has given us a tremendous handle on what is allowed and what is not. To make sense of the universe we live in, we cannot be these Boltzmann brains. We can imagine circumstances in which we were, but that is no way for us to get through our lives. Thank you.